Hello and welcome to this. This is the first lesson in a new topic about the chemistry of amines. So amines are a weird functional group in A-level chemistry simply because you encounter them in lots of other places, not just in the topic on amines, and the topic on amines is typically taught towards the back end of year 13. So it's a strange one because you will have seen things like ethylamine and obviously ammonia and even phenylamine if you've done the topic on aromatics, but it may well be that you haven't done a topic on amines themselves, okay? And so that's what this is all about. So first lesson is all about just sort of general structure, bit of nomenclature, classification of amines, and a good chunk of physical properties, mainly boiling points and intermolecular forces. So let's make a start. Here's your starter questions. I want you to pause the video, do these on a whiteboard or on a scrap of paper. If you're not writing down answers and you are just waiting for them to be shown, you are wasting your time. So pause the video and write your answers down now. Okay, so you should have 4 or 5 answers, right? 3, 4, 5 answers depending on what you could do. Let's have a look at what kinds of things we should be doing. There's the displayed formula for 2-amino-3-hydroxy-propanoic acid, which is less formally known as serine. So this is an amino acid with an OH group as the R group. Well, a CH2 and then an OH group as the R group. The dipeptide of serine would look like this. Okay. Crucial parts about this are that the peptide link is there, the CONH in the middle. Let's have a little look at it. This section. Other crucial parts, the R groups should both be the same. Okay. And then you need an NH2 at one end and a COOH, a carboxyl group, at the other end. It could be that your structure is horizontally inverted from the one that I've drawn. In other words, your carboxyl group could be on the left and your amino group could be on the right. But if you've done that, then that means that the peptide link also needs to be reversed. I could draw that out, but I don't really have room, so I'm not going to. 4 and 5. Okay, so first part of 4, under acidic conditions at pH 3, serine would look like this with a protonated amino group. Under neutral conditions, serine would form a Zwitter ion with a protonated amino group and a deprotonated carboxyl group. And this last question also relates to Zwitter ions. So pure amino acids tend to be solid, and that's because they form these Zwitter ions. And Zwitter ions are ionic. They're strange ions because they have a positive and a negative charge within the same structure, but they still form a crystalline lattice structure with relatively strong electrostatic forces of attraction between the oppositely charged ends of each of these, each of these particles. Okay? So this is pretty standard stuff from the biochemistry topic, which is another place you've seen the amine functional group. All right? Right then, let's get on to the sort of newer stuff. So here's the kind of overview, right? I need you to pause the video and make your notes. So once you've made your notes, right, you've written this stuff down, let's just talk a little bit about the words. So amines can be simplistically thought of as derivatives of ammonia or compounds that are related and similar to ammonia, NH3, but where you take the hydrogen atoms in ammonia and replace them by alkyl groups or aryl groups. So an alkyl group is something like an ethyl group or a methyl group, for example CH2CH3, and an aryl group basically refers to aromatic rings, benzene rings. Okay, so that's what those two words mean. You don't see the phrase aryl an awful lot, and I don't use it an awful lot either. So, amines, like a lot of organic functional groups, can be classified as primary, secondary or tertiary. The way that this works is it's to do with the number of carbon atoms that the nitrogen itself is attached to. So a primary amine has 1 carbon atom in place of a hydrogen, if we're thinking about them as being sort of derived from ammonia, if you like. A secondary amine has 2 carbon atoms, and a tertiary amine has 3 carbon atoms attached to the nitrogen. So we use the symbol R to represent the alkyl or the aryl groups, well, mainly alkyl groups, okay? And we also use the little, tilde or apostrophe symbol to show that these might not be the same. So the best example of this, or the easiest example of this, is to look at the secondary amine. What we're basically getting at is both of these groups could be CH3, or one of them could be CH2CH3 and the other one could be CH3, or one of them could be butyl and the other one could be propyl. We don't know, right, until we actually look specifically at the amine. But that's the idea behind this notation, which you should be familiar with at this stage. Right then, let's keep going. We've got a task. So this is kind of partly a nomenclature task because you have to unpick the name to figure out the displayed formula, and also it's a task that requires you to classify according to what we just looked at. So are they primary, secondary or tertiary? So pause the video and have a go. Okay, so you should have your 4 or 5 structures. Number 5 is kind of a challenge question, so if you didn't do it, don't worry. And what we should find is methylamine is primary, dimethylamine is secondary. If we take it slow and cross-reference these against those generic structures, you should be able to see the idea. That's your CH3 in methylamine, corresponding kind of group. In dimethylamine, there are your corresponding groups, and so on. In this case, the two R's are the same, but like I said earlier, we don't know if that's the case or not until we actually know the name of the amine. It tends to be the case that in A-level you have kind of symmetrical amines where you don't have different types or different lengths of alkyl groups attached to the nitrogen, but you never know. Okay? Right then, let's keep going. Ethylamine, number 3, is a primary amine. Trimethylamine is a tertiary amine. So hopefully you found those relatively straightforward. And then finally, propan-2-amine, or 2-aminopropane, you sometimes see it as called, number 5, is a primary amine because the nitrogen is only attached to one carbon atom. But it looks a little strange. It's there to trick you into saying it's a secondary amine. Because if it was an alcohol, for example, the rule about how you classify it would be different. It would be to do with how many carbons the carbon atom that the N is attached to. You might need to rewind the video to get your head around that one. But if it was propan-2-ol, that would be a secondary alcohol. But because of the way the classification works with amines, this is primary. Is it likely to come up in A-level chemistry? No. That's why it's my challenge question. Right then, let's keep going. So, we're going to spend the rest of the lesson looking at physical properties, specifically boiling points of amines. And the way that we're going to run this is as a series of comparisons. So let's start with one that actually compares an amine with something that's not an amine. If we take methylamine and we compare its boiling point with ethanes, then we see a significant difference, right? Methylamine has a much higher boiling point. Obviously, you don't need to learn these figures, right? I always look them up, for example, but I'm just using them to illustrate something. So, let's do the sort of explanation part first. Methylamine has nice polar functional groups in it. Very specifically, it has one of these. It has an NH bond. It has 2, but it only really needs 1 for this to be relevant. Any compound which has an NH bond, an OH bond, or an FH bond is capable of forming hydrogen bonds. And we typically list hydrogen bonds as the strongest intermolecular force. So methylamine can participate in hydrogen bonding. Hydrogen bonding is the strongest intermolecular force, and therefore that raises the boiling point of methylamine. So then we have to just follow this up by talking about ethane and why we're actually doing the comparison with ethane. So ethane, let's start with why its boiling point is much lower. It's an alkane, so it's a boring non-polar molecule. Therefore, the strongest intermolecular force that influences molecules of ethane is the van der Waals force, which we typically rank as the weakest intermolecular force. And that results in a correspondingly lower boiling point for ethane. So before we move on and look at another example, it's worth pointing out that this comparison is only really valid because methylamine and ethane are of similar sizes. They're not identical sizes, but they have a similar number of electrons. Okay? This matters because you can't just compare which type of intermolecular force there is. You also have to consider the size of the molecules. You'll see what I mean later on if you're sort of a little bit confused. It'll make sense towards the end. For now, though, you might want to just copy the structures. I'm not going to make any notes, but methylamine can form hydrogen bonds. Hydrogen bonding is a stronger intermolecular force. That raises the boiling point because more energy is required to overcome it. By now, at this stage in A-level chemistry, you should be pretty confident with that sort of series of statements, concluding, your statement or sentence with a phrasing about that requires more or less, as appropriate, energy to overcome. Right then, let's move on to our next versus. The next one is ethylamine and dimethylamine. So this is where things get a little bit more nuanced. Okay? Ethylamine and dimethylamine, it should be pointed out, are isomers of one another. You can consider them position isomers, where the amino group has moved from, has relocated from the end of the molecule in ethylamine to the middle of the molecule in dimethylamine. Ethylamine could also be classified as a primary amine, and dimethylamine could be classified as a secondary. Crucially, they both have this. So that's our first comment. And I will make a few notes here because it's starting to get a little more complex. They're going to be very, very brief notes though. Both of these molecules can form hydrogen bonds because they've both got an NH bond. Their boiling points are both comparatively higher than methylamines was in the previous example, but there is a difference between them, and we should probably discuss that a little bit. So there are so many weird fringe cases of, intermolecular forces and things outranking one another. The basic principle really here is we should look at this, and the question you have to ask yourself is, which of these two molecules has stronger hydrogen bonding? That has to be the determining factor because they're, pretty much the same size. So the van der Waals force is going to be pretty much equivalent. But there must be something that's different about the hydrogen bonding in the two of them. So which one is stronger? You should be able to say the answer out loud to yourself. The answer is ethylamine. Because from a fundamental principle, if it's got a higher boiling point, it has stronger forces holding it together. So, the only thing we can kind of suggest about this really is, if the hydrogen bonding in ethylamine is stronger, right, that must be something to do with the NH bonds being on the end of the molecule, with it being a primary amine. And actually, we will have a little look at something else next lesson that relates to this, right? But the sort of simple explanation is, we'll say that the dipole in ethylamine is stronger. The NH sort of, bond polarity might be slightly stronger in ethylamine. And this is to do with the fact that, it's kind of on the end. All right? Again, this is very, very, very unlikely something that you'd be asked about something like this. You could be asked to do the comparison, and you could be asked to deduce which one's got stronger hydrogen bonding, but you're not going to be asked to explain why. It's still a good example, though. All right, let's get rid of this bit, tidy things up. All right, let's keep going. So there's a sort of significant difference between these next two. Our next comparison is propylamine and trimethylamine. So I should also point out, yet again, these two things are isomers of one another. They have the same molecular formula, they're structural isomers, okay? The boiling points are quite significantly different this time. Propylamine is 49 degrees C and trimethylamine boils at 2.9. So there's something kind of crucial that you have to spot here, right? Let's assume that the van der Waals force between these two molecules, the van der Waals force for each of these molecules, let's assume that that is pretty much equivalent. It will be slightly different because of the branching in trimethylamine, but let's assume it's pretty much equivalent because they've got the same number of electrons. What's the key feature that's missing from one of these molecules that's going to influence their boiling points? So you should have thought of or spoken out a suggestion. It's all to do with what's not here. Because trimethylamine is a tertiary amine, there is no longer a hydrogen atom attached to the nitrogen. That means it is no longer capable of, it's not capable of forming hydrogen bonds. That lowers its boiling point because now it's just relying on some kind of permanent dipole-dipole force or the van der Waals force. So, the only thing I'm going to write down here is that trimethylamine cannot form hydrogen bonds, and that's because there is no NH bond in the molecule. This is something that I often reinforce simply because people very, very frequently forget about the idea that you need to have a hydrogen attached to the nitrogen or the oxygen or the fluorine in a molecule for it to be able to form hydrogen bonds. It's not enough just to spot an N or an O or an F. You have to spot an NH, an OH, or an FH. Okay? The way I always remember this is Nhofer, which sounds strange, and it doesn't roll off the tongue quite as simply as Nof, which is what people often teach, but it's more accurate. Nhofer, not Nof. So, no hydrogen bonding in trimethylamine means it's got a lower boiling point. So then a couple more examples, again getting into sort of slightly fringier, more peripheral, weirder stuff. Well, just one more, not two more, sorry. So, methylamine versus propylamine, right? Actually, this isn't that strange. Both methylamine and propylamine are primary amines. They can both form hydrogen bonds. But this time the comparison relies on something else, which is that propylamine is a larger molecule. It therefore has a stronger van der Waals force. So let's assume that the hydrogen bonds that form between molecules of methylamine and the hydrogen bonds that form between molecules of propylamine, let's assume that they're the same. They won't be entirely the same, but let's assume they're pretty much equivalent. The thing that now differentiates them is propylamine is a bigger molecule, it has more electrons, it will therefore have a stronger van der Waals force. And that raises the boiling point. So you might think that that's a strange thing to do, but we'll tie things up by saying, well actually, that's quite important, and the reason it's important is it reinforces something that I said way back here, which was that the comparison of intermolecular forces is often only valid if you are comparing molecules of similar sizes. And what I mean by that is it's all very well and good saying, well, this thing can form hydrogen bonds and this thing can do permanent dipole-dipole, whereas this thing's only got the lowly van der Waals. Well, the van der Waals force can actually get quite strong if molecules get much larger. And so if you're trying to do that comparison, it needs to be between molecules of similar sizes, because otherwise you start to kind of get things mixed up. Let's take just a verbal example. I don't know what the figures are, but if we compared the boiling point of methylamine, well, in fact, no, we can do this. Compare the boiling point of methylamine, the thing that can form hydrogen bonds, with the boiling point of trimethylamine, which can't form hydrogen bonds, and you look at those figures, well, trimethylamine can't form hydrogen bonds, so why is its boiling point higher? And the answer is because it's a bigger molecule to the point where it kind of, it basically, the van der Waals force basically outweighs any kind of hydrogen bonds you can get in methylamine. So this is complex stuff. It's fundamental in the sense that it is year 12 content, but it's very easy to kind of get through the A level without properly understanding this. And to be fair, you can probably get through this topic without fully understanding it. But I do think it's important to try and revisit the concepts and the tricky parts of the intermolecular forces section of bonding and structure, which is why we've done it. So then, next time, base properties of amines.